Welcome to this video presentation, FPGA Verification with VHDL bus functional models. My name is David Clift and I'm an application specialist for First EDA. First EDA is a value-added distributor of electronic design automation solutions in Northern Europe, specializing in software and hardware solutions for electronics design and verification. I'm joined today by Jim Lewis, founder of ThingWorks, principal architect of the open source VHDL verification methodology, better known as OSVVM, as well as being chair of the IEEE VHDL Standards Group. Welcome back, Jim.
Hi, David.
As we discussed in our previous videos, one of the biggest challenges facing FPGA designers and verification engineers today is how do they complete the verification of their vastly complex designs. In this presentation, we'll look at modeling our test environment using bus functional models, sometimes called transaction level modeling or TLM. So Jim, what are the basics of a bus functional model?
So basically, as we're building our environment, our goal is to surround our design under test with the models, with the actual things that it would normally interact with in the system. Okay, so it looks, basically this approach is similar to all other TLM approaches, whether it be system Verilog or any other environment. They all, from a block diagram standpoint, they all look the same. So in this scenario, we have models that implement the signaling to device under test. And those models can be subprograms, or they can be entities. And then we have, what I like doing is having a central model, test control, that contains test code to sequence and or synchronize the model. So for low flow models such as a CPU, where we're issuing CPU reads and writes, we'll just have the actual code in there. For other models that do a high volume of data handling, such as an Ethernet packet or something like that, the synchronization might be go grab the next packet from the file. And then each test becomes a separate architecture of this test control. So as we build our test suite, individual tests are architectures of the test control entity. And again, transaction level modeling, basically what the models are doing then is they're looking at the operations on a CPU read, CPU write type of boundary. Okay, so we're basically telling the models, go do a CPU read or a CPU write, and the model is responsible for the detailed signaling of that interface. So the way I like to look at transaction level modeling then is I like splitting it into two pieces. One piece is transaction initiation, which for me is always done via procedure call. And the other part is the transaction implementation, the simplest version of which we'll do with a procedure. The more complex version we'll do with an entity. The more complex and capable version we'll do with an entity. Then our tests consists of procedure calls. So our tests, whether we're doing a subprogram-based approach or an entity approach, looks identical. We write up sequences of reads and writes, of sends and gets, and we use the procedure calls to initiate transactions. And I like keeping these procedure calls descriptive. So CPU read, CPU write. So they're focused on exactly what the transaction is, increasing the readability of the test itself. I find this simplifies and accelerates writing tests. I think we tend to write more tests this way because it's fun. Okay, if somebody asks us, did we do this? We can either quickly review our tests and know exactly that we did, or we'll write an additional test really quickly to get the job done. This greatly simplifies maintenance. In interface change, we simply edit the procedure itself. So we can quickly roll with changes that become necessary as we go through the design process. It's readable, okay? So we can explain to other members of our community exactly what CPU read and write do, and they can tell what the test sequencing does. If somebody finds a bug in our design, the software guys are using our design and they find a bug, they can go back to the sequences, how we set things up in the tests, and try that out, because more than likely the things that we tested actually work, as opposed to maybe they're doing things in a slightly different order. So to work around, if there are latent bugs in our design, are often in our test bench. Okay, so with the entity-based approach, the transaction initiation is still done by procedure call. But the actual implementation, the signal wiggling, is done by an entity. There are some distinct advantages of this over a simple subprogram approach. First, the model is concurrent, which means we can contain multiple processes in it, multiple different threads, okay, as opposed to a subprogram approach where you have only one thread naturally. It's the subprogram. It can't fork out anything else because VHDL doesn't have any fork capability, okay? But this is really well suited towards hardware modeling, okay? In particular, complicated behavior and or state machines, we can write multiple processes to implement them. In other words, when we code these, we can use either a behavioral style or we can use an RTL coding style to write our entities. In addition, we can bundle all of our functionality into this model. So checkers, result loggers, we can put them all in the same model because we have the processes to support this. Finally, transactions, again, whether it's subprogram approach or entity-based approach, become the base layer for all testing. Directed testing is we just make transaction calls. Algorithmic testing, we write code and call transactions. File-based testing, we read from the file, and we use basic information from that file to call transactions. Constrained random, we use randomizations from the OSVVM randomization library, and then we wrap code around that and we make transaction calls. And then going beyond that, OSVVM has this intelligent coverage capability in which we write coverage models and we randomize across the coverage models. But again, we take that randomization information that comes back from the coverage model and call transactions and simply layer it on top. One of the big advantages of this is that it allows mixing different test methodologies. Going further, transactions also facilitate adding things like functional coverage, self-checking, and scoreboards.
Thank you, Jim. That's really very interesting. And I know from my experience working with certain test schedules for devices, it's quite common to see tests described as transactions on specific interfaces. So this transaction level type testing fits very nicely into those sort of testing regimes. And I would have thought that once you've written your bus functional model for a particular interface, be it a CPU interface or a UART interface or maybe something as complex as an AXI interface, that interface model is usable time and time again.
Oh, absolutely. Beyond that, I like doing what I call pre-use of the models, which is basically try to plan my test environment so that I can use these models also for my RTL level tests and my core level testing, and then finally use them again in my system level testing.
Yeah, I think with today's designs, the size of them, the limited time we have to complete them, being able to reuse code over and over again and not have to effectively reinvent the wheel every time we do a design, it's a great advantage and a boon to productivity. So that's really good.
Yeah, absolutely.
Anyway, thank you very much, Jim, for being with us today. And Jim will be back with us as to talk about using constrained random verification techniques. Is that right, Jim?
Absolutely, yep. Look forward to it, David.
I look forward to meeting up with you again and discussing constrained random. Thank you for joining us in this discussion. Watch out for our next video discussion, which, as we mentioned, is on constrained random verification techniques using OSVVM. If you require further information, please visit our website at www.firsteda.com. Thank you.